So the first couple parts of this are fairly easy. Whenever you're looking at the flash, he's going to have certain forces acting on him. The flash has a mass of m and is initially at rest at time 0. When he hears a damsel in distress, he takes off running straight horizontally with a constant force of F of the flash. So when he encounters this force is going to be a negative RV. The negative is just telling you the direction. So just be aware of your negatives. A lot of times, I'll show you here in a second where that negative comes up. And his velocity is V, and that R value is some positive constant. So for what we've done, you've seen this R value as a K. You've also seen it as a B. It really is just any constant. It doesn't have to be anything specific. So whenever we look at the forces acting on the flash, he's going to have a force that's pushing him this way. That's the force of the flash. He's also going to have a force that is this way. That is going to be the drag that's pushing against him. And then we'll obviously have our two up and down forces where there will be a normal force and a force of gravity, but those two are going to cancel out because of the fact that he's not moving up and down. So whenever we want to determine the magnitude of his terminal velocity, the terminal velocity would be when we look at F equals ma, this acceleration becomes 0. So the net force is going to be the force of the flash minus the force of the drag is going to equal 0, in which case the force of the flash has to equal the force of the drag. And then we can substitute in this RV value and say the force of the flash is equal to R times V. So the terminal velocity is going to be the flash over R value. Now, what I was telling you about with the negative sign earlier is that oftentimes you'll see this equation written as, because this is the net force, you might see it written as the force of the flash plus the force of the drag is equal to ma, in which case when you substitute in, you get that negative RV equals ma. So it doesn't really matter what you make as that negative, as long as you're consistent and know like all that negative means that it's acting against him. So far, so good? Head nods, does that make sense? Okay, awesome. So moving on to the differential equation then, the differential equation, remember, is just a derivative. So whenever we look at this equation, we're looking at the equation to say, well, where would there be a derivative in that equation? And that derivative is really part of the acceleration. Because if you remember, the acceleration is the derivative of the velocity with respect to time. So we can take this equation that is the FF minus RV equals ma, and just simply state that acceleration as the derivative, dv dt. And that's all that they're looking for in that particular case, is that you've converted the acceleration into a dv dt. Now, the next part is the part that becomes really super fun. If you love math, then this is going to be fabulous for you. So we have the force of the flash minus RV is equal to mdv dt. And there's a lot of math magic that happens in this part. So what we're going to do is we want to integrate in order to get the velocity. So we have to put our two velocities together and move the dt to the other. So this is what we would call separation of variables. So I'm going to multiply both sides by dt over m. Multiply both sides by dt over m, and I'm going to divide both sides by this ff minus rv. Ff minus rv. And what that does is it puts my dt over m on the left side, it puts my dv and my ff minus rv on the right side. And the reason that I would do that then is because when I go to integrate this velocity, I need to have my two v's on the same side, and then I just moved the m, because it's a constant, over to the other side. Okay, so the next step then would be to integrate these. If the m is constant, I can pull it out, and remember that the integral of dt is just going to be t. So on the left side, I end up with a t over m. This is technically an indefinite integral, so I would need to add a constant to that. Now, when I look at the right side, there's not an easy way to integrate this The easiest way would be looking at some integral that's saying the integral of 1 over x dx is equal to the natural log of x. So if we can get this, the right term to look like that, then that can be our integral, is that natural log of x. So we're going to use a little bit of math fun here that is called a u du substitution. So if I set this denominator equal to u and say that it's the force of friction, or the force of the flash, minus Rx, minus Rv, then I can substitute in the u into the denominator, and I'm one step closer to that 1 over x value. The problem in the numerator is that this is really a dv, and I need it to be a du in the same terms as the variable in the denominator. So what I'm going to do is take the derivative of this u function with respect to the velocity. Well, what's the derivative of a constant? It's 0. What's the derivative of this term with respect to the velocity? It's negative r. So when I do that, I can solve for dv and say dv is du over negative r, and then plug that back in to the numerator. So I would have du over negative r. From there, it becomes a little bit easier, because if I multiply both sides by negative r, then on the left side of this equation, I'm left with the integral of du over u, and that is similar to that 1 over x dx. So that integral then is going to become the natural log of u. And the left side will still stay the same. Lastly, this is still an indefinite integral, so technically I need to add a constant. So far, so good with me. Head nods for those of you on video. Okay, now looking ahead, I'm going to make this constant be a special constant, and I'll explain why in a second. I'm going to change this to be the natural log of c, and I'm going to combine it with the constant that's on the left, because all of those are constants. They're different constants, but they're still some constant of some kind. Okay. The reason I do that is because if you remember, there's a natural log property that says the natural log of x minus the natural log of y is equal to the natural log of x over y. So I can take this right side and say the natural log of u over c equals a negative RT over m. And what that does is it allows me to take the e function to both sides to get rid of it on that side, and it keeps my constant outside of the e function. Does that make sense? Okay, so another way to think of it would be, if I don't do this, I'm going to write it over here for a second. If I don't do that, I'm going to have negative RT over m equals the natural log of u plus some constant. I would have to subtract the constant to the other side, minus c equals the natural log of u. And now when I get rid of the natural log, I've just embedded or buried my constant into that e function. Do you see what I'm saying? Which doesn't help me nearly as much. So I don't want to do that. I want to make it so that I can keep that constant outside of the e function. So now I get that this is equal to u over c. And I can multiply both sides by c then and say u equals c times e to the natural, or e to that power. Two more steps to go. What I'm going to do then is resubstitute my u value back in, which was up here. So this will be ff minus rv. And then the last step is to decide what is that constant value. So if the flash starts at rest at time 0, what is e to the 0? It's just 1, so I would end up with c equals, and at time 0, if he's at rest, this velocity term is 0, so that constant has to be equal to the force that the flash has. So if I plug that back in, I'm still on whatever that letter was. So I'm going to say the force of the flash, e to the negative RT over m, is equal to the force of the flash minus RV. And remember, the whole thing we're trying to do is we're trying to derive a equation for that velocity. So I want to solve for this V. So I'm going to flip-flop these two terms and say RV equals the force of the flash minus the force of the flash e to the negative RT over m. Then I'm going to pull out this force of the flash, 1 minus e to the negative RT over m equals RV, and I can divide both sides by R to get the equation for the velocity. Now, there's one more step that you could do. You don't have to do it, but if you are astute, you would notice that that coefficient is really the same as, lost my right here. This coefficient here is really the same as that terminal velocity. So sometimes you will see this written as the velocity is equal to the terminal velocity times 1 minus e to the negative RT over m. And then as you go through those four problems, you probably notice that this equation is exactly the same for all four of them, except for this terminal velocity value and whatever that coefficient value is that they give, whether it's K or B or R or whatnot. So far, so good. Head nods, does that make sense? That's probably the most complicated part of the whole problem. And the reason is because of having to do this UDU substitution, which is a more complicated form of calculus, and you haven't really started integrals in calculus yet. So it's just memorizing that that's how you do it. And then later again, Mr. McGee will explain like the reasoning behind it. You can't always use UDU substitutions. You can only use them in certain cases, and this is one of those cases that you can use it. Okay, so then I'm going to erase this. This then becomes, I'm going to keep this boxed form. That's really the beginning of this problem now. Use your velocity to derive the equation for the position as a function of time. So let me see if I can take and move this. So remember that position is really the integral of the velocity with respect to time. So I can take and integrate this equation that's down here, the FF over R times 1 minus e to the negative RT over m with respect to time. And then I can, since I rewrote it, I'm going to get rid of that. This FF over R is not dependent on the time, so I can pull it out of the integral. It's a constant. So I'm going to have the integral, and I'm going to distribute my integral to these two terms, 1 dt minus the integral of e to the negative RT over m dt. Whoops. Then this first term should integrate easily to you. You should remember that. The integral of 1 dt is just going to be t. And the integral on the left is an integral that you're going to have to memorize also. It is the idea that, if I rewrite this in a different color, so the integral of e to the a over bx dx is equal to the flip of the coefficient times the exact same thing again. A over bx. So it would be b over a, e to the a over bx. So when I integrate this guy, I'm going to take my coefficient, flip it, so it would be minus m over r, and then just rewrite the whole thing again, e to the RT over m. Then what I want to do is, instead of saying that this is an indefinite integral, let's do a little bit of math magic and say, why don't we take this integral from 0 to time t, 0 to t, 0 to t, and then 0 to t, and we don't have to worry with a constant then, because we know that it's not a totally complete equation. It's going to be just an equation from 0 to whatever time we get that terminal velocity. So when we do that, remember you would take the final, which is your t, minus the initial. So I'm going to take that whole term again, FF over R, the final, which will be t plus m over r, e to the negative RT over m. minus the initial, which will be 0 minus a negative m over r, and e to the 0 is 1, so that becomes the second term. So these two become positive, then that positive becomes negative, and I would have just that the terminal velocity times t plus m over r e to the negative rt over m minus m over r, and that is my equation for the position. So far, so good. Okay, moving on. When we get down to the graphs then, as you think through this, this is going to be some form of a logarithmic graph because that velocity equation is what we had up here, this fr minus e to the whatever, that velocity is going to increase and then it's going to taper off whenever the object gets close to the terminal velocity. So we would label this as our terminal velocity. We found it up above to be that f of the f over r, the flash over r. This is an asymptote, so technically speaking, the object never hits terminal velocity. It only ever gets closer and closer and closer and closer to it. Then our acceleration is going to be the same thing, where we'll start at an acceleration, and as this velocity gets closer and closer to terminal velocity, that acceleration is going to decrease. And again, it's an asymptote, so it will never technically hit 0. It will only become really close. Then we would label this to say, well, if this was originally the force of the flash minus the drag is equal ma. If I'm talking the initial acceleration, there is no drag to begin with. So my a value here to begin with has to be the force of the flash divided by his mass. And that's going to be the initial a value. And then that would kind of round out the whole problem.